Hey, so my name is Jeil, George, for the friends. I'm from the University of Seoul, not to be confused with the Seoul National University. Today I'm going to present about pseudospin magnetism in rhombohedral multilayer graphene, like segueing the latest advances on fractional chiral insulators in this kind of multilayer graphene systems. Nevertheless, I'll be speaking more about the earlier results that to lay the foundations before I discuss about these spin and bipolarized states in GATT multilayer rhombohedral systems. And for that, I'll be spending actually a good part of the initial part of the presentation for the introductory content. So there's like super experts here in the audience about graphene, so it's almost, well, needless to say, but for the sake of the people that are not familiar, I just remind you that graphene, well, consists of, has two sublattices. It can be represented with this Dirac Hamiltonian in the basis of sublattice pseudospins. And then it has like a linear band dispersion, and we have two distinguishable Dirac modes. And the spins we have in total 4 spin value flavors. The moment we add a second layer, we qualitatively change the band dispersion from linear to quadratic, and when we introduce a interlayer potential difference between A and B, we can open up a band gap. So this will be sort of an effect that we can exploit in bilayer graphene with an electric field to charge polarize or pseudospin polarize the system. And when we move to rhombohedral multilayer graphene systems, we progressively, in the minimal model approximation, go from linear, quadratic, cubic, and so on and so forth. And we progressively flatten the band dispersion, and also we sort of modify the chirality of the bands. So this is the low energy representation of the pseudospinor basis, and the chirality of a Dirac Hamiltonian of graphene, where the arrows kind of wind once when we look in this closed contour, changes to winds twice as much, and when we go up to move on to the binary graphene, and so on and so forth, when we go to tri-layers and 4 layers system. And so this is the low energy representation when we reduce all this complexity of a multilayer or a pentalayer system by leaving out only the top and bottom sublattices and integrating out all these like intermediate high energy dimers by this second order perturbation. We end up with the simplified Hamiltonian where the chirality is proportional to a number of layers, and we can represent this effect of an electric field that introduces different potentials in the top and bottom layers as a potential difference between the sublattices, well, here in this case A1 and B5. And here is again the representation of a progressive flattening of the bands, where when we move to a larger number of layers, therefore increasing the density of states and also increasing the chances for Coulomb interaction-driven instabilities. And so this is a phase diagram of such instability. Well, here J represents a number of layers, again, instead of N. Also an earlier work by a colleague of mine in the Seoul National University, the group of Anna McDonald, and well, it's a very old work. And so here we show, they show that here the graph represents the Coulomb interaction strength, and the y-axis is the carrier density. So for instance, for zero doping, we know that in the case of a single layer graphene or chirality 1 Dirac Hamiltonian, the mean field approximation you expect like instabilities or like onset of an order phase when the Coulomb interaction alpha is strong enough. Nevertheless, for J equal 2 or above, it is possible to show, again, within the mean field approximation, that any small Coulomb interaction would immediately lead to some kind of an order phase, and that order phase would persist to finite doping, provided that the Coulomb interaction is also strong enough. So that's kind of the qualitative difference going from J equal to 2, J equal 1 to J equal to 2. And the kind of broken symmetry that was proposed back then was this layer ferroelectric solution that was also named like pseudospin ferromagnetism or pseudospin ferromagnetic phase, where the charge density from one layer is favored either the top or bottom layer, like spontaneously sloshing and breaking, so to say, the evenness of the carrier distribution. So that effect is represented in this energy breakdown, where the Hartree energy obviously becomes positive when the charge moves, when there is a charge imbalance, like changing the distribution, homogeneity of the carriers. Nevertheless, the total energy becomes negative. It's represented with its black line, thanks to the great gain driven by the exchange in interaction, and mainly due to the intralayer within each layer of this Coulomb interaction. And intuitively, or at least in a hand-wavy argument, you can view this as the reduction in the frustration of these like pseudospin arrows that needs to somehow reduce its total energy and chooses to point in the out-of-plane direction. Therefore, in order to reduce the total energy as much as possible. So this kind of analysis, when you carry out actually this a similar result showing the Hartree-Fock calculation with the black line, and this blue line is the just the usual tight binding calculation, where you add a interlayer potential difference to open up a band gap. We see that there is a difference in this Fermi velocity due to the intralayer exchange that somehow gives the energy gain when it opens up a band gap of the system. And therefore, in the moment you open up a band gap, you also generate different Berry curvatures. That also leads to like a Hall effect. And if you consider the 4 copies that we have in a graphene system, 4 spin valley components, you can choose the direction of the band gaps for each one of the copies, and we can think about like three different phases depending on the degree of charge polarization. So we distinguish the completely charged imbalanced valley Hall phase, or partially charged imbalanced pseudospin ferromagnetic phase, and the charge balance configuration, the so-called pseudospin antiferromagnetic phase. Therefore, so this is a representation of the total energy as a function of applied electric field. So for zero electric field, we would naturally favor the charge balance there, like a pseudospin antiferromagnetic phase represented with this blue line. But then the moment we start adding an electric field, we should end up favoring the completely charged imbalance valley-Hall phase and some like the ferroelectric phase somewhere in between. So kind of this type of, well, this is the same analysis, but then here we're representing the band gap as a function of electric field. And we start from the charge balance, we reduce the band gap, and we increase the band gap slightly. And we, for strong enough electric field, we continuously enhance the band gap of the system. And traces of this non-monotonic behavior of the band gap was found in already almost 15 years ago in these experiments by Miriakovic's group near the charge neutral point of bilayer graphene. Only that, so another interesting feature of this kind of systems is that because of the sign of each one of the spin valley flavors are different, can be changed. They would give rise to completely different Hall conductivities depending on the relative signs. So therefore, for this charge balance configuration, we would have like well, spin Hall or the layer antiferromagnetic phases. Whereas for these ferroelectric phases, we would always have an anomalous Hall effect. And this is the same kind of analysis that is equally applicable for rhombohedral multilayer systems. So in principle, by carefully playing with the electric fields, we would hope that in principle we could achieve these the so-called Hall phase, where we have the anomalous Hall conductivity together with all kind of like a spin Hall and valley-Hall physics coming in simultaneously. So so what happens in experiments is that in bilayer graphene, this kind of effect is very small. And even trilayer graphene is kind of shaky in the sense that like trilayer graphene encapsulated in HBN, it doesn't show obviously band gap, and if it shows, it's smaller than 1 millielectron volts. Whereas for 4-layer rhombohedral multilayer graphene, kind of the expected band gap is on the order of 10 MeV. I mean here expected because well, we have to see how to measure or define the band gap in the system. But one clear signature is that the resistivity increases dramatically. These are experimental results. And when we go from a single bilayer, like trilayer, and 4 layers. And this is a representation of the carrier density versus electric field of the resistivity in color maps. So if you focus on the charge neutral and charge neutrality, we see that we can expect that there is a band gap closure that opens up again when the electric field becomes large enough in the system. And so again, within the mean field picture, this is not qualitatively different, only that the magnitudes are much more important than what we saw in bilayer graphene. So in principle, we might expect like a progressive deviation from the layer antiferromagnetic configuration going to the ferroelectric, so to say, like partially spin value polarized, with a partial reversal of the charge, partially charge imbalance configuration, and going to the completely pseudospin polarized configuration. So, well, this is just work in progress. Some work has been done along this direction that actually addition of very small perturbation of or spin orbit coupling terms can kind of completely change the ground state of the system, signaling that the ground states are very, very sensitive to external perturbations. So here I would like to discuss a little further on the energetics of the spin value polarization that can be achieved in these kind of systems. And one interesting observation in recent experiments is the spontaneous polarization of these spin value flavors when we added carrier doping in the system that has a broken inversion symmetry with an electric field. So this is a configuration where we carrier dope the system and all four flavors are evenly occupied, whereas this P1, P2, P3 represent systems where we only fill one of the spin values, or only two of them or three of them. And depending on how we spin value polarize the system, we will get completely different Hall response. And these kind of observations were first reported in ABC trilayer graphene by Jeil Jung's group. And by measuring like this spin magnetic oscillations, we could count the number of Fermi surfaces and therefore kind of map which type of spin value polarization exists in the system. And these have been also extended to bilayers, more just recently for 4 layers and 5 layers. Very recent report. For 5 layers is likely the system where all these kind of signatures appear most clearly. And again, similarly for 4 layers. But this kind of, some earlier predictions on this spin value polarization were proposed also a long time ago. Here we show that this is a K prime and K value where we carry dope the system. We get a Fermi surface with a broken rotation. And so this is a system where we progressively increase the carrier density.
Can we hear you? There are technical issues. You cannot be heard. The last 3-4 minutes, we couldn't hear you. Is it possible to?
Can you hear?
Yeah.
I think the last 3-4 minutes are relevant, so they are as possible.
Rewind, okay. So are we doing time?
Can you try without a microphone to see if it's better?
So
Michael said that was
right, okay. Actually, I could rewind, but
Michael said that was
right. So all this was kind of a
Michael said that was
so yeah, I just wanted to talk about the mechanisms or the behind these spin value polarization that happens in this multilayer rhombohedral systems, where we have a small carrier doping, it gets homogeneous space. So I just wanted to remind you about some earlier work in bilayer systems, but qualitatively many of the discussed are quite similar. Only the strength is different. The overall behavior is that when we have a very small carrier density, we have both rotational symmetry of the Fermi surface and value polarization. Whereas when we keep increasing the doping in the system, we only get value polarization. which eventually restores back to the evenly spin valley polarized ground state. Well, the physics behind the rotational symmetry breaking can be traced to this angular shape of the Fermi surface when we dope the band edges in the band structure. So that is related with this form of these with the so-called like momentum space exchange condensation that was proposed by well, London and Heisenberg already 17 years ago. And so essentially, it says that the exchange interaction tends to bunch together the states that are close in momentum space, and they like to sort of concentrate and enhance the occupation of those states that are nearby in K-space. That would be like the hand-waving explanation. And it stick to a minimal model. Okay, so we can distinguish that are concave up or concave down. Here we have this inverse compressibility, which is the second derivative of the total energy as a function of density. For these kind of phases, the spin non-polarized pseudospin, let's say the non-polarized phases are favored. So we tend to favor the equally occupied phases, whereas if the energy evolution with density is concave down, we tend to valley and spin polarize the system. And this kind of behavior is shown. We can do the study of energetics from the kinetic energy viewpoint, particle energy viewpoint. These contributions are always concave up, will tend to favor equal occupation of the different valley spin components, whereas if we carry out the calculation at the exchange and correlation level, we are showing the RK calculations. The exchange energy will be essentially the driving force for behavior here. So this is like a complex slide with lots of information. I just want to put a few points. So the top is the Hartree that always shows this kind of concave up evolution of the energy and of this inverse compressibility. So here we are distinguishing the red curve, which has a finite electric field, against the zero electric field. So the moment we have an electric field, we sort of expand the where the inverse compressibility is negative. So all these regions will be sort of favoring of these flavors. And this discontinuity region is the region where the density where we cross the top of the Mexican band structure. So changing from the annular shape to the ring shape. And we can see that the explicit calculations, the phase transition boundaries were these transition, the top of the Mexican shape is crossed, and therefore we have a change in the morphology of the, well, we have changed in the Fermi surface. And well, so this kind of consideration can be further along this line. And just for you to keep in mind is that these transition points are also transition points where, so this is like the total energy difference P4 and P3 states. And then, so actually, these actual transition points are close to these phase transition points where we feel the Mexican hands completely. Okay, so this is a more comparison with experiments. And so the scale, the comparisons are similar, but then of course in experiments we have this large electron hole asymmetry, and we are leaving out many different contributions coming from the remote hopping terms in the band structure. And one particular missing point is that in theory, we see the P3 phase, this P3 phase is absent in the experiment. Okay, so this is a summary and outlook. So we think that these rhombohedral multilayer systems are great platforms for furthering studies of the phases and the spontaneously ordered like fractional method. And we can play with the different substrates that use spin orbit couplings or moire patterns that are added on top of these pristine band structures. So yeah, with these I will be comments and questions if there's any.
Yeah, thanks for the advice. I have a question about your first part of your talk. So probably I missed it, but with your theory, can you extract some strength of the electron interaction from multilayer graphene type some experimental data with your applications?
Okay, okay, so that's some work that we carried out recently, but then actually we haven't. Let me see if I have it in the. It's like had some of that information. Okay, right. So it's not a simple question, the one that you. Okay, so it is possible, so to say. Right. Okay. So we will be playing with, in the simplest model, with the on-site U repulsion, and then perhaps the V1 and V2 for the nearest neighbor Coulomb interactions. And if you can sort of assume a value for the band gap, which again I think it is something that we should discuss, because if it's a truly like correlated rate, whether all these Arrhenius plots for the transport can give you the right estimate for the limited band gap, then of course you can play with those parameters within the mean field theory, well, to give you an estimate for the band gap. So in fact, actually this implementation of the extended Hubbard model by Professor Sonia Wu, yeah, it gives a pretty credible. It gives a credible prediction of the band gap for the 4-layer, 5-layer system. If we assume that the band gaps can be defined in terms of the electric field that somehow changes the resistivity in the system. Okay, I hope that it's a complicated answer to a simple question.
Okay, thank you very much.
Okay, any questions from the Dresden side?
Are we done with questions from that side? I have two very simple questions. First, what do you mean by band gap in the situation when you have metal, start with the metal, you end up with the metal? It can be half metal, quarter metal, but it's metal. And second related question probably is when you do your calculation, do you get the states which are exactly half metal, quarter metal, or the states with partial polarization when the bands are less filled, but there is no completely depleted bands?
Okay, so okay, for the first part, of course, the notion of a band gap. Okay, maybe I used a wrong definition. So band gaps are defined for the charge neutral phase, and then when we're talking about the system with finite doping, and then maybe we should say the distance between the conduction band edge and then the valence band edge. So let's put that. So we need that in order to trigger the spin value polarization, and we trigger that with so that would be the well, the answer to your questions. They say the difference between well, the peaks of the density of states, the multilayer system, and in the mean field calculations, we can obtain the partially filled spin value phases. So yeah, so that's the answer. But for that, we need the long-range Coulomb interaction. So with these kind of like short-range models, it was not possible to stabilize the mean field solution with the partially filled, spin flavor polarized solutions. So that would be the answer to the question.
Yes.
Hi, is there any upper limit on the number of layers in this rhombohedral graphene beyond which, let's say, the spontaneous orbital moments degrades or is washed away, or it's even expected in, let's say, 10 or 20 layers bulk graphite rhombohed?
Right, okay. So well, that's part of research we haven't carried out. So that's a question that we need to try to answer. So I don't know the right answer to that, but experimentally it looks like, okay, we should ask the experimentalists. But 5 layers, 6 layer, at least on the calculation side, 6, 7, 8 layers are still good. So in the minimal model, where you remove all these remote hopping terms, it seems to keep improving, even though, of course, we have effects. We should have screening effects coming from the bulk. And we should also have, in reality, effects coming from remote hopping terms that would probably makes the system worse from 7 or 8 layers onward. But we still have to see. We don't know for sure.
Okay, thanks.
And the final question from Paco.
Hi, great topic. Can you include as well superconductivity? Because you know Gregory Bolovic way back proposed room temperature superconductivity rhombohedral graph.
Whether we can add superconductivity or we can. So actually, I didn't understand the question, but whether superconductivity is possible in rhombohedral multilayer. So you're Paco, right? You're Paco. So actually, yeah, I don't know the answer to your question. So whether like superconductivity in graphite is possible and whether it should appear in the rhombohedral system spontaneously. So okay, I would say why not? Because Andrea Young has already reported those superconducting phases for the strongly, well, for the doped systems. But I don't actually, yeah, I don't know the answer to your question.
Thank you very much.